Hello, Anuji, am I audible?
Yes, sir, you are audible.
Okay, sir, but I'm not able to share my screen.
Mm. Hmm. I'm adding you as a co-host.
Okay, okay. Yeah, that is required.
I'm adding you. If that will help you out. Let's try. Now you are able to. So I'm audible, sir.
Yes, yes, yes. Okay, let me rejoin again. I don't know why it is not. Mm.
Yes, sir. Now you are able to audible, sir. Able to hear, sir.
Yes, is able to hear, but not able to share. I don't know why. Share this host management. Turn on microphone. Meeting access.
So try to join from the different ID. Possible.
To join.
Present now में से देखिए try.
Hmm?
Present now. We'll have fifth word. Present now. Mic, then camera, then turn on captions. Smiley. Then we have.
Sorry, an error has occurred when screen sharing. Can't share your screen. I don't know why it is showing like this.
सर आप अपना जो पीसी है दोबारा बंदर के द्वारा सेट करके देखिए और ट्राई फ्रॉम द डिफरेंट आईडी सर ईमेल आईडी ट्राई फ्रॉम द डिफरेंट ईमेल आईडी
या मैं ऐसे करता हूँ, मैं डेस्कटॉप से ट्राई करता हूँ, बट इसमें शेयर नहीं होगा तो डेस्कटॉप में फिर मैं लिख के नहीं समझा सकता, इससे सब वो हो जाता है। नहीं हो, लेट मी ट्राई
कोई बात
दैट।
नहीं Sir, it is visible now.
Audible also. I'm audible also now.
Yes, sir. Now it's audible. It is also audible. Share entire screen. New queue, yes, sir. We'll open the sales.
But now I'll not be able to use my pen
No,
here in this screen. Anyhow,
yes, sir.
yeah. So good morning, everyone. So
Sir,
here, Dr. Navneet.
just give me 1 minute.
Okay,
We'll,
okay, yeah.
Welcome back to all the participants and welcome, sir. So this lecture of our third day, second lecture of third day is being taken by Dr. Navneet Khanna. He is an associate dean, career and development and promotion of innovation and industrial research, and former mechanical engineering department coordinator at Institute of Infrastructure Technology, Research and Management at India. He has worked as assistant professor at BITS Pilani and also taught at IIT Gandhinagar as an adjunct faculty. He is a specialist in building a strong pool of trained engineering graduates and is involved in solving manufacturing related problems of Indian industries and government organizations. He bagged the Early Career Research Award of SERB, Government of India, and successfully completed the project. He has successfully led 90 plus projects. He 90 plus projects defined by the Indian industries and published 90 plus research papers in renowned SCI, SPEI peer-reviewed journals. In addition to this core competence, he has created several avenues of collaborative work with ISRO, DRDO, IPR, IITs, and renowned institutions in USA, Australia, Spain, UK, France, Slovenia, Poland, etc. Dr. Khanna's name figured among the top 2% of researchers and scientists of the world in a report published by Stanford University, USA, and Elsevier of the Netherlands for the years of 2021, 2022, and 2023. Sir, we are very grateful for you for taking this lecture. Thank you, sir. I will hand over it to you now. Thank you, sir. You may continue the lecture.
Yeah, thank you very much, ma'am. So, good morning to all. So, today's topic of my talk is sustainable cooling and lubrication techniques for machining additive manufactured aerospace alloys. So, basically, in this, I'll be covering some basics, fundamentals, and I'll be introducing you about the techniques which we have developed in our lab. So, let's start. Yeah. So this is Ahmedabad, that is in the western part of our beautiful country, is Gujarat, and we are located here in the Ahmedabad. Yeah, let me come up with this pen. Yeah, and ours is only a 10 years old institute, but we are doing quite good. And the labs which we have established here are the best in the Gujarat, if we compare it with the best institution of any state. Yeah, so before starting my talk, I would like to show you that we are interacting closely with the government organizations. Here in the left hand side, you can see that we are having very close collaborations with Institute for Plasma Research, ITER India, ISRO, DRDO, uh, and also we are working with our small and medium enterprises and small scale industries also. So quite a lot of projects we have done in collaboration with these industries. They are supporting and sponsoring our projects, and engineering trajectories. And we are also collaborating with the fine institutions around the globe. We have collaborations in all the seven continents, On paper, seventh continent is still left, that is Antarctica. So one of my collaborator is still there. So soon we'll be having something, in on paper also. So right now, we are also working in collaboration with the industries abroad also. So they are sharing their problems with us, and we provide solutions to them. And in this thing, we are involving our undergrad students. So that is the important thing which we are doing differently from other institutes. So yeah, so let's start our talk. So this is again the motivation for the research of developing these sustainable technologies, machining technologies specifically. Uh, so one is this engine. Basically, this started when I was doing my PhD. At that moment, I had one beautiful aircraft in my dreams. That was SR-71. That is not. So at that moment, that was the fastest plane. Material which was used was titanium. So here also you can see that this is the engine of aircraft, and if we see the parts, so basically it is having four parts. So right now a lot of couple of parts are being manufactured using additive manufacturing technology also. So one part is this fan section, another section is the compressor. So first is the fan, second section is the compressor, where you are having this you can say low compressor, then high pressure compressor, then we have combustion chamber, third section, and fourth section is the turbine section. So in that you have high pressure turbine and then low pressure turbine. So if we see that 95% of the jet engine weight is made up of these two important alloys, titanium and nickel based. So I am basically here in this presentation, I'll be focusing more on the aerospace sector, right? But these alloys, specifically titanium, is being used in biomedical industry and oil and gas industry. So all major industries, these alloys are being used. So if we see that in the two important sections of this aircraft engine, one is this fan section, we are using titanium alloys, and then in the low pressure compressor, here also we are using titanium alloys. When it comes to high pressure compressor and high pressure turbine or low pressure turbine, basically go for super alloys. So super alloys, when we say, then most of the time using middle super alloys, right? So super alloy is made up of these words super alloys. So we are using different types of alloys, but we say it super. So why we say it super? Just by looking at this graph, which is drawn by specific strength and temperature, you can see that aluminum alloys which we are using previously, may still we are using some percentage of aluminum, but 50% of the aircraft material has been replaced by the CFRP. And CFRP is having good compatibility with the titanium. So that is one of the advantage which aerospace sector gets when we go for titanium alloys. And here you can see that as temperature increases, if you are using aluminum alloys, their their strength, you can say, it decreases with the increase of temperature. And similar is the case with the steel. They are having strength, but it decreases as the temperature increases. But this graph is drawn between specific strength and temperature. Specific strength is, you can say, strength per unit, density per unit weight of the alloy. So when we consider that titanium is the best among these alloys, which are being used in the aerospace sector. So titanium is the best when it comes to specific strength. And the beauty is that it maintains its specific strength approximately around 600 degrees Celsius. Also, and in the parts of, in the blades of, you can say, low pressure compressors also. So we are using titanium. But as we move towards the turbine section or combustion chamber, so temperature increases. It goes beyond 600 degrees Celsius, right? So when the temperature is in that particular range, up to 1800 degrees Celsius, 2000 degrees Celsius in the combustion chamber, So at that we can't degrees Celsius temperature. After that, the specific strength of titanium also decreases. So in those particular situations, then we are only left with nickel-based alloys or super alloys. Super alloys may be cobalt-based or iron-based also, but most of the time we are using nickel-based super alloys, right? We are saying it's super alloy because it is maintaining its properties even at the temperatures, right? For example, we are man, woman, but when I was a kid, then we used to see cartoons of Superman. So man having some, extraordinary powers. So similarly, metals which are having, some which can maintain their properties even at extreme conditions. So those are called super alloys in a layman language. So one of these is nickel alloy. So I think now this fundamentally is clear why nickel and titanium are basically being used in the aircraft engine or jet engines. Is it clear to everyone? Bansal sir, shall we go ahead if the thing is clear? Am I audible?
Yes, sir.
Okay. So another is the increased use of titanium alloys in the different industries. As we discussed, we have seen excellent specific strength is one of the important thing. Another is a very high corrosion resistance. So that's why we are using in oil and natural gas industries titanium a lot, right? But it is having also few good properties. As I told you, it's having good compatibility with CFRP also, right? So these are the things which makes this alloy very important. But in spite of all these things, whether we are making titanium from the conventional processes or using additive manufacturing, SLM, SLS, or VAM, it is having poor machinability, and still it is a big challenge for our industry, right? And what is the challenge? Just a minute.
सर विजिट के लिए आया पीछे
मेरा लेक्चर चल रहा है हाँ. So one of the biggest challenge is its low thermal conductivity, right? So what is happening when the material is having low thermal conductivity and we are machining? So the heat, which generally we study that when we are doing machining, so 80% of the heat is taken away by the chip. But here, in the case of titanium alloy, it's totally different. Because of its low thermal conductivity, whatever heat is being generated, it is going to remain at the tool chip interface, and this increases, this creates a lot of trouble, and it increases the tool wear rate also. Another thing is that low contact length. So the contact length between the chip and the chip of the titanium and the tool is quite less. So we are getting very thin chips also. So most of the pressure and heat is being generated in a very small part. Another thing is its high conductivity. So here I am saying that it is having good property, that it is corrosion resistant, right? That's why we are using it in different industries. So here I am saying that it is highly chemical, it is highly chemically reactive material. So miss why I am saying like this, can anybody tell? Because I am putting here the contradictory statement. So anyone can tell? Let's make it little interactive. You may ask question also anytime. Anyone? The audience is there now, or people are not available? Yes, anyone? So the thing is that
Yes, sir, it is all audible, sir.
yeah. So we are saying that high chemical reactivity means at high temperature. When we are doing machining, so temperature is reaching even more than 1000 degrees Celsius. So at that particular high temperature, the titanium is very reactive metal, right? So this is the reason that we are saying that due to its high chemical reactivity, it is going to have poor machinability. And another reason is this low modulus of elasticity. So because of its low modulus of elasticity, you require very rigid machine tools, right? So here by this video, I'll show you that the effect of these things, it's high chemical reactivity and low thermal conductivity. What happens when we machine titanium in our lab? So this video is filmed by one of my UG student, Darshit. So let me check if we can play. Okay, it is not. So video voice is audible?
Yes, sir. Audible.
So here you can see that when we are drilling, so in this particular zone, you can see some sparks are coming, right? And chips are being entangled also. Now, yeah, so due to these, things, due to low thermal conductivity and high chemical reactivity at high temperature, these kind of things are happening, right? When we are machining titanium in dry condition, right? So I hope that now it is clear that why titanium is called, difficult to machine material. So its applications during our PhD work, we worked on few alloys which are being used in the landing gear of the aircraft. One alloy we were using in the Apache helicopter or fighter helicopters rotors, and this is that use of titanium in oil and gas industry. And due to its this beautiful property, low modulus of elasticity, we are using it in the springs of so cars also, but it makes the racing cars or other cars little costly, right? So these are the different applications wherein we are using titanium, right? But it is having poor machinability. So these are the three different zones. One is the primary shear zone. This one is the primary shear zone. This is the secondary shear zone, and this is the tertiary shear zone when machining is taking place, right? So maximum heat is being generated in this particular shear zone. That heat is taken away by the chip. But in case of titanium, because of its low thermal conductivity, the heat is being, not it's not able to take it away, and this increases the tool wear in this particular zone, right? So yeah, so a localized plastic deformation is happening in the machining, which is strain rate is very high, 10 to the power 6. Increment in temperature is
We
also
can use coolant, sir.
what? Yes. You are right. We can use coolants, and I'll tell you which type of coolants we should use. Right, in the next couple of slides, I'll make it clear because the industry is using coolants. So those coolants are, very harmful, not only for the operators or for the human beings, but also for the environment perspective also, which are being used right now. So there are specific coolants. If you are using those kinds of coolants, so those are sustainable. That they are not. Uh, those are environmental friendly as well as human beings friendly also, and economically also, beneficial than the coolants. I'll tell you in the next couple of slides. We need to use coolant. Dry machining journey is titanium is really difficult. But that we did so that we can tell you what are the problems, right? So another thing is increased tool wear, then degraded metallurgical and mechanical properties of the workpiece. So these are the reasons we need to go for the cutting fluids. Poor surface finish and dimensional accuracy we are getting when we are machining without coolants. And the cutting fluid is used to provide cooling and lubrication action. So first is the flood machining, which right now industry is being used, but in Europe and America they are replacing flood machining with the more sustainable cutting fluids. But still in our industry here in India we are still using these traditional machining technique. But anyhow, as government regulations are becoming more stringent, so in near future definitely we'll have to move towards sustainable cooling strategies. So here in the flood machining, we know that we need a specific pump also, right, to pump the coolant to the cutting zone. So you are pumping it and you are putting it in the cutting zone. So you are putting thousands of liters of coolant in the cutting zone indiscriminately. And for using pump, you are using extra source of energy, right? There's the extra source of energy which you are using to pump the material. Then this particular coolant is being mixed with the chips produced during machining process, and that particular coolant stick with the chip, and then you need to recycle the this particular coolant. And if you want to recycle the chip, then you have to you need extra processes to first to remove that particular coolant which is stuck with the chip. You have to remove that coolant and then you need to recycle, so it further increases the cost for recycling, right? And also these coolants are not environmental friendly, are also not human friendly, because a lot of diseases are being occurred because of these flood machining. So one is growth of bacteria inside the cutting fluid, which produces biological risk to nearby ecology. And as I told you, when it adhere with the cutting chips, so you need to go for chip recyclability, and it increases the requirement of energy and cost also. Then it increments to the pollution, owing to separation of cutting fluids particles into harmful gases at high temperature. And you need more space with energy is needed to recirculate, as I told you, or cycle or store the cutting fluid. So health hazards are a lot, like indigested, inhaled, then you encounter skin problems, skin irritations, respiratory problems are observed, and even cancers is being detected, right? So to work with these kind of issues, we need more sustainable cooling or lubrication technologies. So then we come to this concept, sustainability. So sustainability is having three pillars. So one is the economy. So till now, specifically our Indian industry is basically focusing only on the profits. But as people are becoming more aware by the environment and society, so now the things are changing. So for sustainability, we are having three pillars. First pillar is economy, which we are very well aware how to increase the profits. Second pillar is this, that is the environment. And third is the society, third pillar of sustainability. So whenever we are doing any kind of manufacturing processes, right, we have to consider all these three aspects, right? Under society means personal health or operational safety. What is happening when you are using these flood coolants? So there are always a leakage problem is also there. So it is not safe for the operators also. And environment, we have to consider the carbon emissions also. So we'll consider all these aspects in the coming slides, right? Aspects of sustainability. So then, based on this, then we developed few setups in our lab that is related to cryogenic setups. So basically, to reduce the temperature which is being generated during machining difficult to machine materials, or you can say heat resistant alloys. And another thing which was observed by the industry is that when you are machining composite materials, right? So in that composite machining, people cannot go for flood machining, and they cannot use coolant. We also tried cryogenic cooling technique for machining composites also, because it is also not going to stick with the material, right? So let's see. Uh, so first setup which was developed was using liquid nitrogen. So this was the project sponsored under the Make in India category of Government of India. So here we are using LN2 cylinder. So in the capacity is 200 liters of liquid nitrogen that can be stored here. And the challenge is to put this liquid nitrogen, which is in this cylinder, in the liquid form to the cutting zone, right? This particular zone. So that was the challenge, where you need to design the delivery setup in such a way that most of the time you are getting nitrogen in the liquid form in the cutting zone, this particular zone, right? Which we have already seen. So these are the different equipments by which we measure the response variables. For example, for industry, it is very important. The first important parameter to check the condition of your machining thing is the cutting force, and for that we use this Kessler dynamometer, and to measure the power consumption or energy consumption, we use this Fluke 435 series to uh, energy and power quality analyzer. And then to measure the tool, we use this particular equipment and digital microscope to take the images, and this Taylor Hobson surface roughness tester for measuring the surface roughness which we are getting. So basically, these are the few important parameters which we need to check to see how the machining is taking place when we are using this cooling technique, right? So when we are using liquid nitrogen, so its temperature is around minus 196 degrees Celsius. So that is a very low temperature, right? And as I told you, the challenge is to put the liquid in the liquid nitrogen into the liquid form. And what is happening when you are putting this? So whatever heat is being generated in the cutting zone, it is immediately extracting that heat and evaporated in the environment. And already in the environment, we are having approximately 78% nitrogen. So it mixes with the environment, and it's not, harmful for the human beings. But the problem is that you have to be very careful, because there are some disadvantages or the safety. By taking the simple safety precaution, you can avoid some damages. For example, one is frostbite. So if you are when you are putting liquid nitrogen, then you have to be very careful that liquid nitrogen should not be in contact with your skin or with your eyes for a longer period of time. Otherwise, it can damage the particular part permanently. So with simple safety precautions, we can avoid this, because we are doing this machining from last maybe 6 years. So not even a single case of frostbite has happened in our lab. Another important thing which we must be very careful when we are using liquid nitrogen as a coolant in machining conditions, that its expansion ratio is very high as compared to other gases. It's 1 is to almost 786, means 1 is to 800 approximately. So what is happening when you are putting it? It is extracting heat, right, and evaporating in the environment. So you have to be very careful that it should not, uh, because oxygen quantity should be, there. So it should not be like that it displaces oxygen and more nitrogen is there, because if that condition is happening, then it is not going to give you, even a chance to think, and immediately person can fade up. Even a person can die if the oxygen quantity is less and more nitrogen is there around you. So in that case, we you can use, proper ventilation blowers you can put, so that it can immediately displace the nitrogen which is being, coming out from here. So that is also a normal, safety precaution which we should take. Also, you can use the oxygen meter also, yeah, nearby your machine where operator is standing, so that you can see, yeah, what is the level of oxygen. So we need to maintain that. So that is another precaution we have to take into consideration, right? Then a few other things are there. Lead and frost effect, if you have studied the thermal engineering, provided by, controlling the flow rate of the liquid nitrogen. Right, what is happening, as you have seen, that when you put some liquid on the any very hot object, then that liquid, that bubble, it creates bubble, and it creates a barrier between the surface and the gas, right? So this thing, leaden frost effect, can happen here also in this case, but we generally avoid that with controlling the flow rate of the liquid nitrogen, right? So these are the few safety precautions. If you take care in your mind these things, then it's a wonderful process. So what we did, we made the retrofitted setup in this thing. So we can use our setup in the VMC. Here you can see that we are using it in the VMC. The setup. We use this setup in our turning center also, and this is on the conventional lathe also. And this is another fixture which we have designed here, and this is a multi-jet cryogenic drilling setup for CNC. So this is a retrofitted setup which can be used in any industry for different processes. We can use, right, to SMEs also, for companies which are being used in the aerospace, those who are using in the aerospace sector, right? So these are the basic things which we can use, right? So these are the setups which we have developed, and here I can show you the few couple of videos, and which you will appreciate that how we are using this. So one is this setup. Let me show you. Voice is audible when nitrogen is coming out. You can hear that. So it is audible to you. My nitrogen
Yes,
is
sir,
coming.
audible.
Yes, yes. Okay. Thank you very much.
Yes, sir, audible.
Yeah, fine, fine. Thank you, thank you. So these are the different setups. So this particular setup was developed by one of our undergrad student. So the key challenge is that you need to put where to put liquid nitrogen. That is also a strategy. You cannot put it indiscriminately at any other place, right? So after developing LN2, the problem which we face, that it's really difficult to handle liquid nitrogen. You need a lot of skilled labor to handle that particular thing. Although a lot of benefits are there, even the tool life we improved more than 400% also in few alloys. We machined almost all the alloys and composites also, right? And very high productivity, very high efficiency at very high cutting splits. So that is the advantage which we got. And then it comes to, after developing this, then we also think, why not to use CO2, which is already available in the atmosphere, right, for the advantage. Then we compress that CO2, we discuss with the industry, those who are, using the CO2 as an industrial waste. So that is the beauty. Although CO2 is a greenhouse gas, but we are not producing it. We are already taking it from the environment or from the as an industrial waste, and we are using it for the machining purpose. So here also we got, a lot of benefits. So that is the, you can see, that is the, instead of LN2 cylinder, we are using CO2 cylinder. So here the liquid nitrogen is coming out, or liquid CO2 is coming out instead of liquid NN, liquid nitrogen, right? All other benefits are same. And the important thing is that when you are using liquid nitrogen or liquid CO2, you don't need pump, right? As you need in your machine tools when you are using coolant. So energy consumption is also reduced. This makes it, sustainable. Another thing is that when you are recycling the chip, so in the conventional processes, you first need to unstuck the cutting fluid, which is, stick with the chips. So here it is not stick with the chips. So recycling is also, can be done easily. So here also you save a lot of energy. So all these things make it, sustainable process. So here you see that when the chips are, continuous, so it creates a lot of trouble. But here it is compressed, and at 56 bar. So this carbon dioxide is stored in this at 56 bar, and at 56 bar it is coming out. So at very high pressure, it is, instead of when we are putting it in the cutting zone, so the chips which are continuous, those chips becomes brittle in nature. So actually not brittle, we can say discontinuous chips which we get. So industry also requires such kind of things. So we are getting the advantages of cooling of liquid nitrogen, as well as due to very high pressure, we are also getting very small chips, discontinuous chips. So let's see how we are getting. Yeah. So this is the case of 17.4 PHSS, one of the project, and one of the project which we got from one industry. So they want us to machine thin wall component of titanium. So here we use those. So it's a thin wall component. So we are using it with LCO2. Yeah. So I hope that now this setup is also clear. If you have any doubt, you can ask me. Any doubt? Okay, I show you one more video. So in that it was a turning center. Here is a VMC. So here you can see that whenever we are doing machining, we are having a group of students and operators also, because simultaneously you need to fetch values of cutting forces, power consumption, and you need to operate the machine also. So you need a group of people to work on these technologies. So here is very important. Now I tell you about this PV diagram, PT diagram. Here you can see that what we are doing in the case of carbon dioxide, we are using liquid carbon dioxide at 57 bar, right? And it is in the liquid state. So when we are injecting it in the cutting zone, so all of a sudden what is happening? You are 57 bar, with that pressure you are injecting, and it is immediately coming to atmospheric pressure. right? So immediately it is coming to atmospheric pressure, then due to Joule Thomson effect, its temperature, which the liquid carbon dioxide which was stored at 20 degrees Celsius, it comes to minus 78.5 degrees Celsius. And due to this effect, we are taking the advantage and we are extracting heat from the cutting zone. That is the beauty, right? Although it is a greenhouse gas, but as I told you, why we are taking its advantage, because we are using the it as an industrial waste which is already there, and the industry from where we are taking it is, getting that CO2 from the industrial waste. So that's why this process is very much sustainable. And this is the PT diagram for liquid nitrogen. So here it's, very difficult. Here the window is very small, you can see. So you have a very small window with you in which you need to work. Otherwise, it will go to gaseous state, and gaseous N2 is not having good heat carrying capacity. So we need to work only in this liquid zone, and that's why it's a bit difficult to work with liquid nitrogen as compared to liquid carbon dioxide. Also, you can see the temperature of liquid nitrogen is, quite high as compared to LCO, right? So that's why nowadays we are also planning. Although liquid nitrogen has a lot of other benefits, right? But not all small and medium enterprises can't, purchase or can't invest such a high capital cost initially. So we are working for small and medium enterprises by using this particular setup, and for high-end engineering companies, you can go for LN2. So any doubt till now? Anyone? Anji, Dr. Bansal, any student is having any doubt till now?
Any query from panel participants? Can ask anyone?
So if no doubt, then let's move to our next setups which we have developed in our lab. So now we'll be discussing about MQL and EMQL. MQL you already know, you'll find a lot of papers. We'll discuss in brief, then I'll come to EMQL. So the setups which we have discussed till now is basically sustainable cooling methods. Now the setups which I'll tell you, these are mainly for lubrication techniques, right? And then we'll combine both to get advantage of both the things for the hybridization. So this is a minimum quantity lubrication technique, right? So it's a FRL unit we are using, filter, regulator, and lubricator. So it is made up of these three things, right? Filter, regulator, and lubricator. So what is happening in flood machining? We are using, very high amount of cutting fluid, but when it comes to minimum quantity lubrication, it uses 20 to 30 ml per hour, right? So you can see that the quantity is quite less. That's why we can say that it is sustainable as compared to our existing technology, right? So this is a setup, very small setup which we have developed, and we are getting very good results, right? So this setup includes lubricant reservoir, as you have for flood machining, a pump you need so that you can pump the, air from here, and pressure regulator is there. A spray nozzle is required, right, which delivers lubricant directly to the machining zone. And we have integrated this particular unit with our CNCs. So here we use cutting oil as 90% soybean, 5% antioxidants, 5% extreme pressure additives, and this was the viscosity at this particular temperature. So this is a basic setup that is already there in the literature. You can study how this particular FRL unit works. I'll not go into that detail. So This is the experimental setup for MQL process. So this is specifically designed for small and medium enterprises. So you can see that in our lab at a simple stand, we have put this FRL unit, and then we first tested it, calibrated this thing by different nozzle angles, right? Where we are getting the optimized results. So once optimization has been done, and then we conducted the experiments. So this is the one of the software image software. On that we here you can see that this is the silicon wafer. Here we are putting this mist on this silicon wafer by optimizing the distance and angle of this nozzle droplets which are there on this silicon wafer, you can see. And these are the image of droplets after thresholding, right? So how we have done, so that is there in this our paper, right? You can go through this paper, and if you are any doubt you can discuss with me for any research purpose. So these are the results of optimization, right? We use different flow rates in ml per hour, and then the number of droplets which we found on the silicon wafer, then average size of droplets, smaller the best, and then percentage of area covered by the droplets, so that we can achieve the maximum amount of lubrication. So we found that in the fifth experiment, when we maintain the flow rate at 14 ml per hour, we got the maximum number of droplets and the least size of droplet, each droplet, and maximum coverage of area. And then we chosen that this is the best flow rate for our particular condition, that is 14 ml per hour. Because what happens if you are not doing research, then I would like to tell you that if you are budding researcher or you are planning to do research in future, for each and everything whatever you are selecting, you must be having a reasoning for that. You can't say that randomly I chosen the parameters, right? For selecting the parameter, just before selecting the parameter you have to conduct a lot of experiments to reach to the parameters which we are using. So as you have seen the setup, there's a different nozzle. Here you can see that in this setup, yeah, we made these small channels so that we can change the distance, this particular distance, nozzle distance. So we varied the range between this, and optimized value we got was 30 mm. So in our paper, once these values are optimized, then we are now using these values. So nozzle angle we varied from 15 degree to 75 degree and found that 75 degree is the best. And flow rate we also varied from 2 to 20 ml per hour, and we found that this 14 ml is the optimized value. So once the values are optimized after conducting a lot of experiments, at least all these experiments were repeated 3 times, so as to reach to these values. So once these values are finalized, then we conduct a lot of experiments. So another setup which I showed you was EMQL. So in that, what we do, it was just you can say little advancement in the minimum quantity lubrication. In that, the lubrication was, we did the electrostatically charged lubricant we were putting here. So this is the setup of EMQL, and we have put it in the pin on desk turbometer, right? And we conducted the test to find out coefficient of friction, weight loss in pin, and area of wear marks, so that we can finalize the electrostatic voltage. So at different electrostatic voltage we conducted the experiments, initial experiments, to finalize the input parameters. We conducted with the same thing. So we found out that number of droplets were maximum in case when we are using 20 kV electrostatic voltage, and average size of droplet was least in that particular case, and maximum percentage of surface area was covered by this particular. So we decided that 20 kV is the best for our experiments, And these are the results of tribological performance at different electrostatic voltage. So here you can see again that the tribological performance was also best for the case of this particular electrostatic voltage, right? So here you can see that the coefficient of friction was 0.027. That was the least among all other electrostatic voltages which we used. And weight loss in pin in grams, you can see that it was also least, and area of wear mark was also least in this particular thing. So after conducting all these types of initial experiments, we reached to this conclusion that electrostatic voltage, that is 20 kV, is best. And then we started our experimentation. We also optimized the percentage of concentration of hybrid nanofluids. What we did after developing MQL and EMQL setups, we tried to use the nanoparticles also in the cutting fluid to get the further maximum, output in terms of, machining output. You can say that. So we used the graphene hybrid nanoparticles. One was of graphene and another was of Al2O3. We combined that in the fluid, and then we find out the contact angle and coefficient of friction. Right. So here you can see that as the percentage of graphene and Al2 was increasing, so coefficient of friction was decreasing. Right. Here also we found this similar thing, that the contact angle is also decreasing. This is the contact angle here, you can see in this finger. Right. So yeah, optimization of weight percentage of nanoparticles in base fluid. So mix in different concentrations, and then we checked all these things. So in EMQL, I can show you how we calibrated the setup. In this video you can see. So here you can see that oh my god, just a minute. Is it visible, my slide?
Yes,
Yeah,
sir.
yeah, okay. Yeah. So this is the combined setup, you can see, right, for EMQL and MQL. So here MQL setup is already there. This FRL unit is there. Here you can see only the addition of this power source is there, right? We are adding this so that we can charge the cutting fluid particles when it is coming out through this nozzle, and they are making, actually what is happening when we are putting MQL mist droplets in the cutting zone. So suppose there are 1,000 droplets, and few are not entering into the machining zone, cutting zone. So out of 1,000, 500 is going here and there. So when we are charging these particles, then they are, due to charge, they are entering exactly into the cutting zone. So it increases the efficiency of the process. And we found that our tool wear rate, surface finish is better in case of EMQL as compared to MQL, right? But power consumption is more because of this power source we are using, right? So we also developed electrostatic lubrication, but this was not suitable. We reached to the conclusion after doing life cycle assessment that this particular setup is not sustainable. But I can show you how we developed this and how it was working. So charged, here we are not using mist. Here the cutting fluid is directly moving to the cutting zone. Quantity of the cutting fluid is very less as compared to the flood machining. So here you can see how the setup was working, but we are not using right now. So here you can see clearly that due to the charge, this very thin, you know, not layer, but we'll say that this cutting fluid in very small quantity is moving this path. Is it visible now? Directly going here. But when you are using flood machining, you are putting liters of coolant from everywhere. So this was the was beautiful setup, but the results we didn't get very good result. Yeah, but we tried at least. Yeah. So this was the case of separate lubrication techniques which we have developed and the cooling techniques. So any doubt till now? Then I'll come to hybridized techniques, right? People are using hybridized, we are further hybridize it. So any doubt till now?
Query from the online participants. Sir, I have one query. Sir, there any any material specified in which we have used the MQL and EMQL?
Yes. After doing, yeah, definitely. After doing a lot of experimentations, we reached to few conclusion that where to go for MQL and where to go for these cooling techniques. Because everywhere you can't go for only lubrication techniques, specifically when it comes to machining in cornel and titanium, right? Yes, we have reached to a lot of conclusions. I'll share with you.
Okay, sir.
Yeah, definitely.
Okay. Query.
So, yeah,
Okay, sir. You can proceed further,
okay,
sir.
yes. Then comes ultrasonic assisted turning. So, here you can see that we developed this setup in our lab. So, a lot of students from different institutes like IITs are also coming to conduct experiments in our lab. So yeah, so this is a normal setup which you can find in IIT Delhi or some other setups where they are using ultrasonic assisted turning. But what we did, we further hybridized this setup by using MQL technique. So UAT is there already there. With UAT, we combined the MQL, advantage of MQL, and plus in few cases LN2 also, LN2 or CO2 you can say. So we took the advantage of these three in one setup and further improved the machining efficiency. So here I can show you the initial setup which we designed for our conventional lathe. Just a minute. I think here video is not working. Anyhow, so here the vibration was taking place, and here you can see that, yeah, here we are using LN2 jet. So we are taking the advantage of this UAT setup. Already it improves the machining performance. We already know from the literature, and our setup was also working in a good manner. But we further hybridize it with LN2, and we further improve the machining performance. Then after doing this, what we did, we tested it with MQL. Once we got advantage, then what we did, we took UAT on one of the, you can say, on the rake face, we put LN2, and on the flank face, we put this MQL. So all these three things we also used to further get the best results. So you will find a couple of our papers in Tripology International where we got the further improved results by combining all these three technologies into one, right? Then now we come to additive plus subtractive manufacturing. So I'll tell you that whatever we have done in our lab, a couple of works we have also done in collaboration with Professor Anil Singla and Professor Anuj Bansal from Slide also. So here you can see that our UG students are preparing one cylindrical workpiece with the help of VAM for conducting turning experiments. Yeah. So this setup is not based on the CMT technology. So yesterday you had a very good lecture from Professor Sai. He told about the CMT technology of Fronius and other technologies where VAM is based, wire arc additive manufacturing process. So this particular video is not based on CMT technology, but the lab in slide we have CMT technology. So that is a beautiful technology, and it is making better work pieces as compared to the conventional these welding setups which we are using. So I hope that CMT technology is clear to all of you. Yeah, so this is the setup. I forgot to mention here in this slides, but this setup is at slide logo one in Professor Anu's lab. So here you can see that the chamber designed by them for making the titanium workpieces TI6L4V, right? So this is a beautiful part which they have prepared, and now we are doing machining. Although we have done machining on this, and soon we'll be having paper on that, right? So quite beautifully you can see that just by using the wire cut machine we got the final plate. And the thing is that once you are having the final plate, you need to, if the assembly processes are there, then you need to go for the drilling processes, right? So that is the very much basic requirement. So that's why we are conducting a lot of drilling experiments, right? Yeah, so few results I am presenting to you, and it's also a quiz for you. So here you can see that we are comparing result of TI6L4V parts while doing machining. We are getting circularity results, power consumption results, and cylindricity results. One for cryo and green is for flood. So here you can see that circularity results are better for when we are using cryo, and similarly it's better for cylindricity results and also for power consumption. Now it's quiz to you. So why we are getting better circularity results, why we are getting better cylindricity results, and why we are getting better power consumption results as compared to flood machine? Can anyone tell me? And D1, D2, D3 are three different drill bits which we are using, and for all the drill bits almost similar results. So anyone would like to tell me why we are getting better results in cryo as compared to flood?
Anyone?
Yes.
Anyone? Please give any answer.
Sir, how many students are there? Let me check.
So is temperature the one of the reasons?
Okay, one of the reason is temperature. Okay, what will happen? Temperature is less than why you will get better circularity and cylindricity and power consumption. Just make a guess. Will not go into very technical, but at least you can guess. You are right that we are using this due to cryo, but why?
Tool wear may be lesser, so because of that
Okay. Yeah, one reason it might be the one of the reason. Your cylindricity is that circularity is that you are getting the circular near to your ideal diameter, right? And cylindricity is when you are increasing it to the complete hole. So we are measuring at different points circularity, and then we achieve the cylindricity. Okay, one reason is very good. Yeah, due to lesser tool wear, that might be one of the reason. Okay, good. And what about power consumption? Why we are getting better power consumption results with lesser power consumption in cryo? I told this during my lecture. If you have heard it carefully, then you can tell the answer.
In flood machining, we need to recirculate the coolant. For that,
Yes, very good, very good. What is your name, beta?
Karthikeyan, sir.
Karthikeyan. So you are correct. So here we need to use extra motors, right, in flood
Yes.
machining. So that adds to additional power consumption. Very simple and a basic you can say common sense answer. Very good, very good. Okay, let's move ahead. So the cost incurred while drilling VAM, CN, TF as compared to raw titanium. Okay, so I'll now throw few important things regarding LCA also before closing my lecture. So we say that we do not inherit the earth from our ancestors; we borrow it from our children, right? So keeping this important thing into our mind, we are also doing the life cycle assessment. Now, what is happening in the manufacturing, right? So suppose you are having this Mother Earth with you, so you are first extracting material from the earth, right? So first phase you can say this thing we are taking from Professor Jawahir's lectures, right? So first thing is the pre-manufacturing stage. P means pre and M I am saying it manufacturing. So pre-manufacturing stage where you are extracting the material, do a lot of pre-processing things to keep the material to make the material ready for manufacturing, right? So this is the first step. Actually, I don't have my iPad was not getting connected. That's why I don't have pen here in the desktop. Otherwise, I am perhaps I am using now mouse to make this thing. So that's why it's little difficult. So second stage after pre-manufacturing stage is the manufacturing, which we people are doing since which you are studying from your BTech, right, from the first year. So that is the manufacturing stage where we said manufacturing is conversion of raw material into the finished good. So raw material is the pre-manufacturing stage, which we are getting after doing a lot of processing from the minerals which we are getting from the earth, right? So this is the second stage. Once manufacturing has been done, then what we do? We use it, right? Whatever product we have made. Once we use, then the final stage is the disposal stage. We use it and we throw it back, right? But we don't think that what is going to happen. So that is the traditional way of uh, using the products. But now in our new project which we are doing with one of our partner from UAE, we have recently got. So we are using the circular economy concept in this traditional chain, right? So already Professor Jawahir has developed the concept of 6R. So what are those 6R? If anyone can tell, initially it was lean manufacturing. So in lean manufacturing, we are using 1R concept. So was reduce. We need to reduce the waste from all the processes. Yes or no? And then with the concept of green manufacturing, we came up to 3R concept. What were those 3R? Reduce, recycle, and
Reuse.
reuse. Yeah, so those were the 3Rs which came in with the concept of green manufacturing. Then the concept of sustainable manufacturing, which we are discussing today. So that was related to 6R. So those 3Rs were there. We added 3 more Rs. So what were those 3Rs? One was recover. Recover. So for example, you are doing using aircraft, right? And instead of making the complete aircraft from the old aircraft which you are retiring the aircraft, you can take few components, recover those components and in the aircraft, right? Another R was redesign. You can redesign the component and then you can remanufacture. remanufacture. So these 3 R's further they added to make it a 6R approach. Now in circular manufacturing approach, what we do? Anyone? Before getting the product disposed of, we again make it into the another life cycle, right? Means we are recovering the product and we are reusing it. So instead of disposing it, we are again adding into the another life cycle. So that is a circular manufacturing. So one component can be used for different life terms. For example, when a lot of people got retired, so from suppose from one bank they have got retired from nationalized bank, then they join some private bank. So actually they are not getting disposed of, they are again coming into some other life cycle. So that is a new concept, and we do life cycle assessment in our lab right from the extraction from the mother earth till its disposal or further into the in another life cycle also. So there are different approaches for doing the life cycle assessment. One is, for example, you said from cradle to grave, cradle to cradle, cradle to gate, gate to gate. So different approaches depending upon your requirement of the industry. We use such kind of life cycle assessments. So I hope that there must be some disturbances as the one meeting is going into my another chamber. I have asked them to slow down, but anyhow, they are. I mean, so yeah. So how we do? We first define goal and scope of our work, right? Then we do the inventory analysis. Then we conduct the impact assessment, and then we interpret the results, right? So these are the 4 steps of any life cycle assessment. So in goal and scope, we define definition of used approach, whether we are going for cradle to grave, gate to gate, cradle to cradle. Then we define the goal of life cycle study, assessment study. We define the functional unit for quantification of impacts. We define boundary presenting a relationship between input and output flows. And we list down the assumptions which we are making for our life cycle assessment. So all these things we doing, we complete these tasks in goal and scope definition. First step. Then we list down the inventories which are involved in the life cycle assessment, data collection and calculation for foreground as well as background processes which we are considering. Foreground is, for example, we are drilling, how much power we are using, that we can calculate from our data. Background data, if you don't have any data with you, then for example, you can take data from other literature also, right? So that is not your own data which you have generated, right? Then we conduct life cycle impact assessment. It includes the selection of methodology and impact category, association of life cycle inventory results assigned to impact categories, category indicators, or then we go for normalization of results. Then we interpret the results and we identify the significant issues, completion check through sensitivity or uncertainty analysis. Then we conclude and we recommend whatever we have observed from our study, right? So there are 18 midpoint impact categories which are affecting the environment. So 3 important things are there in life cycle assessment, that we say that 3 endpoint categories. One is human health, then ecosystem and resource availability. But these further 3 are distributed in, initially in 18 different categories, right, which are affecting the respiratory problems, various types of other diseases, and which are affecting your ecosystem, resource availability. So we use different softwares: OpenLCA, EcoChain, Mobius, SEMA Pro, Gabi. All these are different, softwares to analyze the life cycle assessment. But it's a kind of black box. So your data should be very accurate. That is the most important thing, because you are going to give some input, you are definitely going to get some output. So your input data must be, very accurate. So that's why whenever we do life cycle assessment for industry, so there no problem. We get the accurate data from the industry, but whenever we do research in collaboration, then it is very important that how accurate data is being provided to us from our collaborator. So it all depends upon that, that how the better life cycle assessment we can do for their processes. So we did this small life cycle comparison of additively manufactured Inconel 625 as compared to TI6L4V. So this is a plate manufactured using wires of Inconel 625, and this is for TI6L43. So here we found that we did this analysis using EcoChain, and Mobius gave us provided us the data. We are thankful to EcoChain Mobius for providing us their software facility for conducting this. And we calculated the carbon footprints, that this much of carbon dioxide equivalent weight is being produced when we are manufacturing 1 kg of TI6L4V, right? So this much of percentage breakdown was there. Out of this 16.6 kg, 66.6 percentage was involved for primary production of titanium. So actually the main increase of this impact on global warming is due to the manufacturing of titanium itself. Well, not manufacturing, the production of titanium from its ore. So that is the main power consumption source which we found out from our research. And while producing this Inconel 625, you can see that it's 9.18 kg CO2 equivalent weight, and it's 16.616 kg. So more carbon emissions are there when we are producing TI6L4V as compared to Inconel 625, right? So this is a basic study for one of our undergrad student we did, and then we will now going to extend it for machining also. So basically you can see that this primary production of additive manufactured TI6L4V, so that is taking the major amount of carbon emissions. That ore mining, mineral separation by using titanium dioxide purification, then titanium tetrachloride production from Ti2. This is the manufacturing of titanium alloy, right? Then we go for secondary process, hot forming, and then VAM process, wire drawing, deposition, and by using argon gas, right? So this is the one of the case study. I think I'll be sharing if required. This case study you can go on your own, or if time is there, then I can tell. If any question till now, first tell me. Then I'll tell this particular case study which we presented at 28th Syrup LC conference. Any doubt?
Any query from the online participants? Anyone?
Okay, if no query, then I'll quickly go ahead with this one small case study and I'll finish my lecture. So this case study was presented in this particular conference. So wherein we took one particular alloy VT20, this code is of Russian category code VT20 of titanium alloy. It's alpha titanium alloy, right? And we use the drilling process using 5 coated solid carbide drill, and these were the 4 different techniques. One was dry machining, one was flood machining, and C was LCO2, and this D was LN2. So 4 different techniques we used, right? Cooling and lubrication techniques for just for comparing the life cycle assessment. So these are the 4 steps which I told you: goal and scope definition, life cycle inventory, impact assessment, and result interpretation. So we did the LC analysis for these 4 different machining techniques in this paper. One is dry, another is flood, third is LCO2, and fourth one is LN2, right? So we first find out the cutting energy. So that included the energy component due to thrust force and energy component due to torque. One is thrust, another is torque. And we calculated the total energy, that is energy due to power, right? To use these simple equations for finding out the cutting energy. One was due to the thrust component, and another is due to the torque, right? And energy due to power is directly we can just by multiplying the power with the time, we can calculate the total energy. So here interesting things came in this paper. You can see that with the help of dry machining, we were able to only drill 20 holes before reaching the tool wear criterion. With flood coolant, we were able to drill 142 holes. With LCO2, it was 202 holes. And for by using LN2, it was 292 holes. So you can see the huge, increase in the tool life when we are using these techniques, LCO2 and LN2, as compared to specifically flood machining. And also these techniques are sustainable, as we have already discussed now, right? Another thing is less energy per hole was there when we are drilling it with LCO2 and LN2 as compared to flood and dry. This is another advantage which we get, right? And one is less energy, another is this number of holes were more, right? And then we did the life cycle analysis. So what first was the goal? So goal here is to compare the four cutting fluid strategies. Scope is streamlined LCA. Here the functional unit of this product system we considered as one hole, which is having 5 mm diameter and depth was 3.5 mm, and the material was VT20 workpiece material. And we had some assumptions while doing life cycle assessment. So here you can see that foreground processes we defined background processes, and few processes we excluded from evaluation. So you need to be very much careful, and you have to tell the audience that what are the foreground processes, what are the background, and what are the processes which you have not evaluated. So that was our first case study, and at that moment we excluded the used drill bit and recycling of chips. But in our recent studies, we have included these also, right? And also production of titanium plates. So this was the first study. That's why we left that. But slowly, as we had a lot of tie-ups with industries and other collaborators, so we get data from specific data of these things from our collaborators, right? And background processes like cutting oil for flood machining, these we took from the either from the supplier or from the literature, right? Production of LN2. This data was not generated by us. Foreground processes, emulsion production from tap water, these thing, and electricity generation for drilling a hole, etc. We calculated all these things on our own, right? So few things we calculated from the data available to us, and few things we took from the literature or suppliers, and some data was not available with us, so we excluded that particular data. That was the initial study, but right now we are doing complete life cycle analysis. We have almost all the data. So this is the life cycle inventory. So here the process of quantifying energy and raw material requirements, atmospheric emissions, waterborne emissions, etc. So we did, as we have seen in the previous slide, electricity generation. So database was electricity production, photovoltaics, lantern roof installation, eco-invent cilia. We took this, and LCO2 production again from eco-invent. So here you can see, yeah, production of LN2 and LCO2. So this data we got from eco-invent, and some data we took from the literature, right? So after declaring all these things, then we did the impact assessment, and for that we use Mobius eco chain, and they provided us the complete data, and we are thankful to them. And then we established a linkage between the product or process and its potential environmental impacts. And the methodology which we used was Recipe 2016 midpoint. And midpoint impact categories are of higher accuracy and comprehensive, while endpoint results are concise, right? At endpoints, only 3 results are there. And midpoint categories were 18, as I showed you in the previous slides, right? So that's why they are more accurate. Then life cycle impact assessment was calculated for 18 categories for each cooling strategy, right? So these were the 18 different categories, and we did the assessment for all these 18 categories for each strategy. So we got these results, right? Human health, you can say the least is being impacted by this much. So yeah, so the results were that we got higher values of cutting energy and the total energy for dry, flood, and cryogenic environment using LN2 as compared to LCO2. So yeah, so more number of holes were drilled using LN2, and this much of higher values of cutting energy and total energy have been found by dry, flood, and cryogenic environment using LN2 as compared to LCO2. So here you can see that LCO2, you're getting the least results for energy consumption and for cutting energy also. But dry machining is economical, but we were able to drill only 20 holes. So you can say that it is environmental friendly, but production rate is very less because of poor chip evacuation, and there are a lot of challenges which was reported regarding the surface integrity. That's why you can't say that dry machining is should be used, right? Because production rate is very less. So a lot of time will be go every time you need to change the tool. It will affect the productivity, right? As well as the workpiece quality. So although it is environmental friendly because no harmful things are happening when you are doing dry machining, but it is not economical from this point of view. So it is not satisfying the one of the pillar of sustainability. Yeah, so these are the different things which we found out, and yeah, so these are the old slide that we have published a couple of papers on flood machining LCO2. So maximum number of papers we published 21 of using LN2, but right now I hope that we have crossed it using LCO2. This is a little 1 year old data, so right now more papers on LCO2 we are publishing. So these are the few of my PhD scholars who have completed the PhD, few of my undergrad students who are working in good places around the globe. Yeah, yes. So few of the current students, but now they have also become the past. They have joined universities in US. Yeah. So these are the few publications from our work, quite few, not all, from our lab. So thank you very much for your listening.
Any queries from the participants?
गुड आफ्टरनून सर, कैसे हैं सर?
बस बढ़िया खन्ना साहब, बहुत ही अच्छी टॉक थी। मैं partially, although I could attend only partially.
No problem, sir. No problem. At least students.
I have one query that you mentioned somewhere web-based this life cycle assessment.
Which one, sir?
By web-based platform you have used for
Yes, sir. Yes, sir. Yes, sir. EcoChain Mobius we are using right now.
Have you any slide which is giving us idea that what are the inputs for the 18 different categories of web-based assessment?
Sir, I have put couple of slides. Let me show. Yeah, only this much I have put here.
Okay.
For our piece, which you sent me, additive manufacture TI6L4V. Actually, we have some connections with EcoChain Mobius. So
Okay.
they have provided us free access. Otherwise, very costly. So they have provided us whole, their database.
Okay.
The database is the key actually. The
Okay.
more accurate the data you are having. So, sir, we did all these things. Primary production, how much carbon emission would be there? The argon gas which you provided us, that how much liters we have used. So on that basis, we calculated that how much this carbon emissions are happening. So wire drawing process, how much? So after making all these things, we reached to this, that while producing 1 unit of this TI6L4V in your lab, this much of carbon emissions are being done.
Okay.
And this is higher as compared to Inconel 625.
But how that platform is reaching this value, detail is known to us, or it is inbuilt in the platform?
So they are having database with them that if we are producing, if we are doing, suppose this step, suppose when we are doing ore mining, so how much carbon emissions would be there?
Okay.
So this data they are having with that.
Okay.
So, and they have calculated, they have taken maybe from different industries, those who are involved in such kind of processes.
Mm-hmm.
So that's why the accuracy is there.
Okay.
Yeah. So that is more important. And how much carbon emissions would be there when you are separating from TIO to purification.
Mm-hmm.
And then for each step they are having all this data.
Okay.
Yes.
So any other query from the participants? Okay, if that is, then Khanna Sahab, I think this was a very good session, and all the participants which are there in the offline and online mode, they must have benefited from it.
Okay, thank you, sir.
We are already associated with you, and hope that in future also we'll be organizing such events.
Sure, sir.
Thank you, Khanna Sahab. Thank you.
Thank you very much, sir. Yeah. Bye, sir.
Bye. Dr. Sanat Agarwal, are you there online? So, participant, we can here break for the lunch, and after lunch, I think we will meet at 2:30. Thank you very much.
मुझे बता दें, मैं यहाँ से एंड कर दूँ, मैं लिख दूँ एंड द नहीं एंड द कॉल फॉर एवरीवन कर दूँ यहाँ से।